Hi, everyone. We can use matrices outside of systems. We can use matrices just as boxes of numbers, like we often do in statistics. So let's talk about matrices in general. And these won't even be augmented matrices for the most part, just boxes of numbers like these. Oh, these represent numbers. So some notation. We often represent a matrix by a capital letter, like capital A, capital B, and so forth. This says that the matrix A consists of entries that we can label as A sub I j, where I is the row number and j is the column number. So for example, in this 2 by 2 matrix, and often in linear algebra, Math 254, you would write out this kind of notation. In the upper left, A sub 1, 1, row 1, column 1, row 1, column 1. A sub 1, 2, row 1, column 2. A sub 2, 1, row 2, column 1. A sub 2, 2, row 2, column 2. Now for huge matrices, which you might consider more abstractly, you might use columns. For example, if you have you could have, for example, A sub 10, comma 10, if you have a 10 by 10 matrix. Although I'm sure you wouldn't write out all the entries explicitly. Now, A sub 1, 2 and A sub 2, 1 are not necessarily equal. If they are, then we have a symmetric matrix. Here's an example of a symmetric matrix, which is extremely important in higher math and linear algebra. Not so much in our class. So for a symmetric matrix, the idea is that when you look at the main diagonal, right, the entries that face each other across the main diagonal are equal. So the threes here face each other. Symmetric matrices are extremely useful in higher calculus, statistics, and so forth. They have great properties. Okay, finally, when does A equal B? Before, with our ER rows, we were doing row equivalent matrices, but when are two matrices actually equal? Well, A equals B if A and B are two matrices, if and only if they have the same size, m by n, and they have the same numbers or expressions in the same positions. So for example, here, these are both 2 by 2 matrices. Upper left has 1, upper right has 2, lower left has 3, lower right has 4. Same numbers in the same positions. So if you look over here, even though these two matrices have the same entries, they're in different positions. Two of them are in different positions. The 2 here and the 3 here, they switch positions, which means that these matrices are not equal. They have the same entries, but in a way in a different order. Two of them are in a different position. Now, if this is the matrix A, then there is a relationship between these two matrices, and we can describe the relationship as the transpose relationship. If this is A, then this is A transpose. And why is that? Because the rows of one matrix are the columns of the other matrix. And the rows here are the columns here. Over here, if we consider these as matrices, this matrix is 1 by 2, and this matrix, is 2 by 1. Now, sometimes we might think of this as a row vector, and sometimes we might think of this as a column vector. And by the way, these are transposes of each other. Incidentally, what kind of matrix is equal to its transpose? I'll give you a hint. We've seen one before. This guy over here. If you make the rows the columns, well, you get the same matrix. You get the same matrix, right? So this matrix is its own transpose. That defines what kind of a matrix? Defines a symmetric matrix. You don't have to know that for our final, but in linear algebra, Mat 254, that can be a useful fact. It will be a useful fact. It's the way that you can succinctly define symmetry, a symmetric matrix. Okay. Next up, we're going to talk about basic operations for computing with matrices, and they're not so surprising. Next time.